Hi everybody. I want to talk a little bit about spatial dependence and autocorrelation. This is kind of an intuition building exercise. By doing all this stuff, I'm trying to get you a deep understanding of what's going on rather than just kind of memorizing the meaning of these terms and understanding their application. And I'll start out by just describing a spatial interaction function. Now imagine if I had to simulate. I needed to create data, and the data are distributed in space, so they've got locations on the surface of the Earth. They're geocoded. They've got coordinates, let's say. And at each location, I need to generate some sort of attribute. So at each location, there's an attribute. And I want the attributes to be clustered. I want the attributes to be clustered in space in such a way that neighbors are kind of similar to each other. Now, there's lots of ways to generate data that have that property. That's actually fairly easy to do. I want to start out by talking about the spatial interaction function. So the first thing I need to do is write this little function. It probably already exists in some other form in R, but I wanted to just create a function. And this little function here, what it does is it calculates a spatial interaction by, it's used to create a spatial interaction by turning a distance, this thing measured on a continuous scale from 0 to infinity, let's say, and turning it into a probability. So it takes a number, and it turns that number into a probability. The larger the number, the smaller the probability. The smaller the number, the larger probability. So what it basically is saying is that, and the number, imagine that the number is distance. Large distances, small probability. Small distances, large probability. This kind of makes sense if you're to look at something like the spread of information, where you're more likely to have information spread between two people if they're close to each other, if they spend time close to each other, they're neighbors or they work in the same workplace, than if they're far away from each other. I'm very unlikely to be influenced by somebody who lives in China that never communicates with or travels to Canada, and I never travel to China. So that the likelihood of us influencing each other is astronomically small, whereas somebody who lives next door to me or works in my workplace, the probability of our interactions influencing me are relatively high. So this is just a function. So it's just a mathematical function that's turning a number into a probability, and that's the reasoning behind it. And I won't get into the details of it beyond that right now because it's not really important. Now, the next thing I do is I create a series of points, and the points have three attributes, basically. I'll just show them to you. One of the attributes is the x-coordinate, and one is the y. It's the position of the point in space. And v is some other attribute. We can think of it as anything. It could be each point could be the location of a home, and the attribute could be the price of the home. The attribute could be the square footage of the home. It could be any number of things. But basically we have a spatial coordinates, which represent its location in space, and some other attribute. So I've created these points. And then the next thing I do is I want to conceive of these points in what's called a distance matrix. There's many ways to represent it, but this is the way I'm going to do it here. So every point has a distance to every other point. And what I'm doing is I'm calculating these distances and putting them into a table, into a distance matrix that looks like this here. So each point, so point 1, this is point 1, point 2, point 3, all the way up to point 100. So I've got 100 columns, and I also have 100 rows. So this is a symmetrical matrix insofar as the columns are labeled from 1 to 100, and the rows are labeled from 1 to 100. And there's this diagonal, and the diagonal represents the distance of a point to itself. So point 1 is 0 distance from itself, which makes sense. A point is 0 distance from itself, right? And then every other number is the distance between the points. So the distance between 1 and 2 is 2.62. The distance between 1 and 3 is 0.47. Not all distance matrices have to be like this. They can be asymmetrical. If you have, let's say that you have 2 points in space in a city, and there's a one-way street, so that you can travel. The travel time between the points is, or the travel distance is, 5 kilometers, but because of one-way streets, the way back is 7 kilometers. So it's conceivable that distance matrices are not symmetrical like this, but this is a very simple distance matrix. So basically it tells us the distance between each point in space. Now, what I've done is I combine the information from this distance matrix with this spatial interaction function up here that I already described to you to turn all of the numbers into probabilities. So all these distances are going to be turned into probabilities. And that's what this is. This is another matrix with probabilities assigned. What it's basically saying is telling us, it's giving us a probability. And in fact, I'm going to call this a spatial interaction probability. The probability that the 2 points will interact in space. Now, I'm assigning a value of 1 for each point to itself, basically saying that every point will interact with itself, which is trivial. And it's not necessary, but you can do it. And every other number has a probability, and that probability describes the likelihood that that 2 points will interact. So here it's saying that there's a roughly 1.3 in 1,000 chance that 1 will interact with 2, 7.4 in 1,000 chance that 1 will interact with 3, and so on. And there's all these probabilities. Some are higher, some are in the 20% range or 30% range, but many of them are very low. So that's a probability matrix that's derived by taking those distances and combining them with that spatial interaction function up here. Now I want to create a spatial pattern. So right now all the data are random. Basically, the points are just random in space, and the attributes are completely uncorrelated with location. But I want to change that. I'm going to do it by imputing some dependency in the data, some spatial dependency. And I'm going to do it, and I want you to think about it as though it's kind of a contamination or a spread of an idea. So all these points, let's say we could pretend that each point is a city. And all of a sudden, I'm going to create an idea, a new idea in a city. And then we're going to see how that idea, and then that idea will be spread from city to city. But the probability of its spread will be related to that P matrix that we created. So basically, it'll be inversely proportional to distance. Any city that's close by is likely going to have an idea spread to it from the germinating city. So if let's say Toronto is where the idea emerges, cities that are nearby it are more likely to have the idea spread to them, and cities that are far away are less likely to have the idea spread to them. For one of the points, I'm going to randomly select a point, and I'm just going to give it a much larger value. Then I'm going to have the neighbors interact with each other, and their interaction is proportional to that probability. So every point is going to get a chance to interact with every other point, but its interaction is going to be proportional to that probability. And what's going to happen is I'm going to have several rounds. This is going to simulate the process of interaction. In fact, I'm going to have 10 rounds of interaction where this new idea has come out to a city, let's say, that's one of the points, and then I will simulate multiple turns or rounds of that idea spreading. And in fact, it's somewhat animated. You may not see it very clearly here, but it'll be somewhat animated. If you look down at this window, as I run this function, it'll go 10 times, and it's going to spread an idea from one city to another. And as you can see, it spreads it by basically taking the value and taking this value and then combining with the city that it's interacting with. So let's say a new idea comes out in Toronto. We just call this an idea. We just give it a number, the number 50. And then that idea interacts with another idea in another city. And so both cities get the average of that idea. So this is all representing ideas with numbers is not very intuitive, but you just kind of have to suspend your disbelief and imagine that you could represent an idea with a number. And so these two cities interact, so the product of that interaction is some averaging of that idea. And what we've got is now a map which has been contaminated really at the start with just one idea. So one change in the attribute in one city, one point, and then that's just spread throughout the map over time in a way that's proportional to distance. Now this is the process. One of the challenges is that in the real world, we don't really know how many processes work precisely like this. Usually they work through a combination of different things, not just a process like this, but a combination of processes. It's hard to measure it, and it's even harder to predict it. But there are some ways to represent the degree to which this pattern is spatially dependent, and one of them is this idea of one of the ways to do it is through what's called autocorrelation. And I'm going to manually here calculate this autocorrelation. And the autocorrelation is basically telling us the degree to which observations observations that are similar tend to be close together. So let's say, look at housing price. If you had a housing price, how often are houses that are expensive near houses that are expensive? And how often are they near houses that are inexpensive? Or is house price just randomly distributed throughout the city? I mean, we all know from experience that it tends to be clustered in a way, that houses that are expensive tend to be near each other. And so what we're doing is spatial autocorrelation is one of the ways we can measure, a very simple way, the degree to which there is this pattern of similarity in an attribute over space. Now, I'm going to create a matrix here out of these data just for speed issues. And then we're going to do a little bit of programming here, which I won't really describe it. Basically, it's using an indexing procedure to efficiently go through the data and create a nearest neighbor matrix. So here, there's several different steps involved, but basically what I'm doing is I'm creating a matrix that we can then use to calculate this measure of spatial autocorrelation. So I won't really describe this. It's similar to what I've already done, actually, so I'm not going to worry about it too much. Now, we have what's called a neighbor matrix. It indicates which points are considered close to each other. There's a lot of different ways we can do it, but I just arbitrarily said you pick for any given point, it's got 4 neighbors. They're the 4 closest points to it, and that's what we're creating as a neighbor matrix. Once we've got a neighbor matrix, you can actually have this calculated automatically for you in R. I'm just doing it manually here. And then you can go through the process of actually calculating spatial autocorrelation. And spatial autocorrelation is very similar to the idea of correlation, generally speaking, except instead of 2 variables, you've got a single variable and many locations. And so it's a slight change on the traditional measures of covariance or correlation, and it's basically just a way of taking into account the fact that it's a single attribute, but it's measured over many locations, and we're looking to see the degree to which that attribute is similar to the degree to which that attribute is patterned spatially. And at the end of the day, we get this calculation of Moran's I. We get this calculation of Moran's I here. And this calculation gives us a value, and depending on how it's scaled and depending how precisely how it's calculated, but it could be between a positive value of 1 and a negative value of 1. This particular indicator suggests a very high degree of spatial autocorrelation because it's very close to 1 for this particular measure. This is where it's typically scaled to be between -1 and +1. If it's close to 1, it's highly spatially autocorrelated. And that's kind of what we would expect to see because these data were created for that reason specifically. But if I make one minor change here, let's say I go in here and I just get rid of this process. So I change this value. We can probably lower the degree of spatial autocorrelation a little bit by just getting rid of this randomly generated point. Let's just try this again. We should still get some spatial autocorrelation at the end of the day. Yeah, we still got a fairly high degree of it, a fairly large amount of spatial autocorrelation. And in this particular case, it's just because all the variables are, there's still a lot of if you wait long enough, you can always create the pattern of autocorrelation using this process that I've generated here, no matter what the starting point is. At any rate, what we see here is a pattern, a way that this spatial pattern can be represented. And I think what the takeaway here is to get an intuition for the whole process, the process of how data are created, the idea of a spatial interaction, the way we can simulate the process of spatial dependence, and we can do it a number of different ways. We can seed the space with a contaminated value like I did the first time, or we can just let it run, and what you'll do is you'll get kind of a clustering of observations over time, even if the originating conditions were random. So you can get a very non-random pattern, even from random starting conditions, just because of the non-random nature of distance, the fact that we tend to interact with things that are close rather than things that are far away, so we get a little bit more structure. So that's a bit of a lengthy video. I'm going to try to edit it down a little bit so it's not as long as it appears to be right now, but I'm hoping that gives you some intuition about spatial interaction. All right, thanks. Bye.